I mean, one of the puzzles in the apartheid era was the members of that government were members of the Dutch Reformed Church. So how does a church person do that kind of thing, which is a very old kind of problem? One of the things which I've been very strong about is fighting fundamentalists. They're fundamentalist scientists who try to say that science can answer all the deepest questions of meaning in the universe. That's a whole lot of rubbish. I've thought very carefully about what science can and cannot prove.
Yeah, I mean, I know some very well-respected physicists who believe in the multiverse.
Yeah.
Yeah.
But there are respected physicists who believe in string theory. And string theory, there's not the slightest evidence that string theory is true. If you don't believe that there is an absolute standard, you cannot say, for instance, that apartheid was wrong in an absolute sense. You just have to say they believed it was okay and other people believed wrong, and you have no way of choosing between them. What's going on in the Gaza Strip at the moment, you're not able to say either side is doing something which is morally wrong. All you can say is, I don't like what they're doing, and I do like. And to me, it's an absolutely fundamental part of existence that we should be able to say that something is wrong factually.
Today, I talked to Professor George Ellis. Professor George Ellis is an Emeritus Professor from the University of Cape Town in South Africa. He obtained his PhD from the University of Cambridge in the United Kingdom. And I invited Prof. George Ellis today on my channel really because he has been trained in math and physics, but has taken this expertise to investigate questions of morality, ethics, spirituality, and religion. And this is something he touches upon in this episode. We talk about a couple of things, and some of them being whether or not morality is something that we discover or invent, or in other words, whether morality is sort of bedrock reality, there's a bedrock reality of morality, or it's merely a social convention. We also talk about whether or not mathematics is discovered or invented. Here's some very interesting opinions there. So if this is your first time here, may you please consider subscribing to the channel, liking this video, and interact with me in the comment section below. I hope you enjoyed the episode. Professor George Ellis, it's really a pleasure to have you here on my channel. And I'm sure I'm going to have a great time talking to you. And I hope you have equally a great time. Thank you so much for agreeing and welcome. So the first question I usually ask my guests here is for the people who don't know them, tell us more about who you are, where you were born and raised, and how you think your upbringing and the kind of interest that you had as a child sort of brought you to the career that you eventually followed.
Well, I was born in Johannesburg, lived there until I was 12 and moved to Cape Town. And I studied at UCT, mathematics, applied mathematics. Then I went to Cambridge, studied general relativity, cosmology. I stayed there till 1973. Then I came back, head of applied maths at UCT. And I've been there, except I've traveled a lot. I've been a visiting professor in Texas, Chicago, Boston, Hamburg, Alberta, London University. I've been visiting professor many places. Oh, and in Trieste at the place called CISA, the International School for Advanced Studies.
Yeah. So what do you think, when during your childhood did you start becoming interested maybe in science in general and physics and mathematics in particular?
I was lucky enough to have a really good physics teacher, a really good mathematics teacher, and I was just a natural in those areas. I've always been fascinated in how things work, and in a sense my whole career has been trying to understand how things work, starting professionally with cosmology, but then moving through to, I got interested in the philosophy of cosmology. Then I moved through to trying to understand biology and the brain. And I've been working in those areas, biology, the brain, complexity, how complexity works. I've been doing that for about 15 to 20 years.
Yeah. That's an interesting thing, because it leads right straight into my next question, actually, which is your training really is in mathematics and physics, but you are also interested in and have done work that has to do with morality, ethics, spirituality, and religion. I
Yeah.
don't think that's a very common combination, right? Like for someone who is a physicist and a mathematician and go, knee deep into these topics. So what do you think led you there?
It's a complicated story, but when I came back to Cape Town, 1973, apartheid was at its height, and I started a research group in my technical area, UCT, but I got very involved in anti-apartheid work of a theoretical and practical nature. I got involved in a whole number of organizations, and I started thinking about morality. I mean, one of the puzzles in the apartheid era was the members of that government were members of the Dutch Reformed Church. So how does a church person do that kind of thing, which is a very old kind of problem? But I had met in Cambridge a very, very nice guy called Bill Sturger, who was a research student and he was a Catholic priest and a Jesuit. And he got me involved in some debates about science and religion. And I went to many meetings on that topic, and then I wrote a book about it. So I did quite a lot of work on the science and religion interface. And of course, there have been some people who've said that they contradict each other, and that depends how you understand them. If you're a fundamentalist, yes, they are contradict each other. If you have a more sophisticated understanding of religion and so on, then they're not incompatible. And one of the things which I've been very strong about is fighting fundamentalists. They're fundamentalist scientists who try to say that science can answer all the deepest questions of meaning in the universe. That's a whole lot of rubbish. I've thought very carefully about what science can and cannot prove. And in cosmology, you run up against some of those limits. For instance, despite what some of my colleagues can say, science cannot tell you why the universe exists or why it has the nature it does have. Those are meta-scientific questions, metaphysical questions. They're beyond. There's no experiment that can tell you why the universe exists.
Yeah.
There's no experiment that can tell you what existed before the universe exists. And of course, that's a paradoxical statement, because the word before cannot apply to the universe before it existed. You get tied up in metaphysical problems. But in any case, as a scientist, I have a very strict distinction between it's scientific if you can test it by observation or experiment, and if you can't, it's not science. And so I've run up against some of my scientific colleagues, and what is very strange is there's quite a number of aspects of what's labeled itself theoretical physics nowadays, which is not actually scientific. It's making statements that cannot be corroborated, and one of the most famous of those is the claim that a multiverse exists, and I've got into debates over that. If there were to be a multiverse, other universes like ours, you can't see them, you can't interact with them. I can say anything I like, you can say anything you like, and we can have a debate, and it's not science, it's a philosophical debate.
Definitely. That was actually one of the questions I was interested in asking you, whether or not you believed in a multiverse. But you have, of course, clearly stated.
The critical point is the word believe. You see, if it was science, the word believe would not be there. So even using the word believe proves that it's not science.
Yeah, yeah,
I,
definitely.
I hasten to say that in the Oxford University philosophy of science department, there are quite a few people who do believe in multiverses, but that's
Yeah. I mean, I know some very well respected physicists who believe in the multiverse.
yeah.
Yeah.
But there are respected physicists who believe in string theory. And string theory, there's not the slightest evidence that string theory is true, and it's a bit disturbing when people push stuff under the banner of science and or physics when it's not it's not testable. You can't prove it's true. And okay, so fine. There's a boundary. There's stuff we have established.
Mhm.
There's stuff we haven't established, and there's stuff which we would like to. And the boundary of what we know is forever extending. And there's nothing wrong with make theories beyond what we've proven. That's perfectly fine. But one must be quite clear about what state that stuff is, whether it has been established, is a theory which might be established, or is just a very vague speculation. And I think that's quite crucial.
Well, yeah, I understand what you mean, and but I'd like to sort of push back on what you've said about these physicists that you call fundamentalists, right?
Yeah.
That they are making claims that are not scientific and would not be testable. Um, so I suppose what they would say is, then what should we do? Should we, if there are things that we cannot investigate using science or using physics, does that mean then they would say, should we make bad arguments that come from religion that are not good enough? Or should we be comfortable with not knowing? That's what they
Uh,
would.
well, look, firstly, you can make philosophical arguments that got nothing to do with religion. So you can do metaphysics. One of the metaphysical issues you can discuss is whether religion is true or not, and there's various kinds of arguments there. But by definition, religion is about faith. Faith. The whole point of faith is that you don't have evidence. That's why it's faith. And you can argue various ways why you think religion is true or is not true. Um, but it's but what is a mistake? And some scientists have tried to say science proves religion is not true. Well, that's simply that is not a true statement. And in fact, it's been known for a very long time by serious philosophers that you can't, in a serious sense, prove God does exist, but you can't prove does not exist either.
Yeah.
And that's not a scientific question, and it's not a question for which philosophy can establish a definite answer. Philosophy can give you arguments one way or the other.
Yeah. All right. So another thing I'm interested in talking about is I've heard you mention 5 categories of things that you consider exist. May you please tell us those things that you think exist? I think I may have some questions to ask you about those.
Which categories do you mean?
So you mentioned things like, firstly, particles.
Yeah.
And then you mentioned things like sort of like the possibility space of
Yes, correct.
yeah, of physical constants, I suppose. Yeah, those 5 categories.
Okay, well, the thing is, if you start looking at what underlies cosmology is what I call possibility spaces. So, for instance, there's possibility spaces for physics. You can't move faster than light. You can't violate energy conservation, and so on. If our current understanding of physics is true, there are fascinating biological possibility spaces. And there's a wonderful book about this by a guy called Andreas Wagner. For instance, there are possible proteins. There are possible maps, phenotype to genotype maps, and his book Arrival of the Physicist is a great discussion of that. there are possibilities in physiology. One of them is, for instance, if you take a rabbit and scale it up 10 times, a 30-foot rabbit, it can't exist because there are scaling relations, and the weight of a 30-foot rabbit would crush its feet. It's structurally impossible. So there are biological possibility spaces. The interesting ones is there are possibility space for mathematics. I'm a mathematical Platonist, and there are mathematical Platonists insist that mathematics is out there and we learn about it, we don't invent it. So that nobody invented the number pi, we discovered the number pi. Nobody invented Pythagoras. Well, again, Pythagoras' theorem is something you discover because you're discovering a real relationship out there. And one of the possibilities, there's chaotic dynamical systems. We didn't know they existed. We found they exist, and so on. So one explores the space of mathematical possibilities, and this is contrary to some people who claim we invent mathematics. And the key point there is to understand the space of possibilities is timeless, eternal, it's unchanging. What we know about it varies with time and place. We didn't know Pythagoras' theorem was true, then we did. We didn't know that there were chaotic dynamical, then we did. And so the mistake people make is mixing these two things. The actual Platonic space of mathematics and human understanding of it. This one depends, is changing all the time, and this one doesn't.
Yeah, just because.
Yep.
Yeah.
And then the very, very interesting one is these are thoughts. And if you think about it, there are spaces of possible thoughts. And there's a statement that goes like this: you can't think a thought unless it's possible to think it. Now, you may think that's a very silly statement, but actually it's a very, very profound statement. It's about whether the statement you make makes logical sense. If it doesn't make logical sense, and there's a space of logic.
What would it mean? Sorry, Prof. What would it mean for a thought to be impossible to think?
Well, it could be self-contradictory. It could be. Let me mention that there's a wonderful book by a guy called Louis Borges called the Library of Babel, and in the Library of Babel, it contains billions and billions of books, and in those books is written every possible sentence which can be written down in those books. And the point about this, which is the key point, is that this library is finite. And the reason it's finite is the following: for a sentence to be a sentence, it's got to be meaningful. It's got to convey a thought from you to me. Otherwise, it's not a useful sentence. Now, short-term memory's got 7 slots. And that means if the sentence is more than a couple of thousand words, it won't convey any information from you to me because you can't remember the beginning by the time you reach the end. And in fact, a meaningful sentence is probably 49 words. Let's be generous. I'll give you 490. I'll give you 49,000. But the point is, it's finite. And a lot of linguists make a serious error. They say you've got to remember that sentences can be infinite. That's a load of rubbish. They have that a sentence has to be meaningful. And linguistics, parts of linguistics, have simply forgotten the whole issue of languages to do with meaningful stuff. And so I've got to remember the beginning of the sentence by the time I reach the end of it. And that means, if we're generous, we can allow 490 words in a sentence, let's say. But you can, in principle, print out a computer program and can print out all possible sentences. In that sense, all possible thoughts are finite. And all those possible thoughts existed in some sense before the universe existed. The fact that you could think those thoughts was there already. And then the really deep thing is the following: those possible thoughts include thoughts about good and bad, love and hate, all that kind of sort of stuff. And so those kinds of thoughts were already there in some sense in these possibility spaces, which I call the deep structure of the cosmos. Now, I'm not talking science, obviously, I'm talking philosophy.
Yeah, yeah. You also have a last one, which is the one of morality, I think, right?
Yes. Yes, well, this takes us all one stage further. The fact that there's this possibility space for thought, one can then ask the same question with mathematics. A mathematical proof is either right or wrong. It's out there. That's a statement of the way things are. Now, with morality, there's this very, very old question: is morality absolute or is it relative? If you have one set of morality and I have another, is there some way of distinguishing with them? Can we say that something is, as a matter of fact, right or wrong? Or can we say it's only different cultures think it's right or wrong? And this is an absolutely crucial thing in life today. I'm a moral realist, and exactly the same thing applies there. You must distinguish morality as it is and ethics as society understands them. And ethics, society has had all sorts of understanding in different places and times and so on. And what I claim is that some ethics is a real representation of what is actually right and wrong, and some is not. Now, if you don't believe that there is an absolute standard, you cannot say, for instance, that apartheid was wrong in an absolute sense. You just have to say they believed it was okay and other people believed wrong, and you have no way of choosing between them. What's going on in the Gaza Strip at the moment, you're not able to say either side is doing something which is morally wrong. All you can say is, I don't like what they're doing, and I do like. And to me, it's an absolutely fundamental part of existence that we should be able to say that something is wrong factually. It is wrong. And I think this is a crucial part of nature. And so I add, and I've said some. So there is an abstract space in the space of thoughts there's an abstract space of thoughts of what could be right or wrong, but I'm saying is on top of that, this is a major step further. In that space of possible thoughts, one can, in fact, determine some that are good and some that are not good, that some are evil and some that are not evil. And that's a stance which I take, and I know quite a lot of people disagree with me, but if you don't make that statement, you cannot make any statement about the Gaza thing. All you can say is, I don't like it, or you can say it's wrong. But if you're a moral relativist, all it means is you don't like it.
Yeah. So when it comes to that, so with mathematics, right? So it seems like you're also a Platonist in the sense of morality.
Yeah.
In the case of mathematics, we sort of have a way of discovering these truths, right? Like discovering, we can sort of investigate whether this statement is true or false.
Yes.
In the morality sense, I think it would be a bit difficult to try to, how do we, come close to this possibility space, try to understand it and discover these truths?
Some people try to say that morality comes from evolutionary theory, but evolution is, it can lead you to feelings about morality, and you must distinguish feelings from what the actual thing is. And in order to do it, you have to engage in meta-analysis. You have to stand back and think, is it really right or wrong? And you have to try to get criteria for this, and you have to try to get understanding of the nature of morality. And I've got a spectrum of morality, which I talk about from time to time. And on the far left is the truly evil. It's the people who will kill, torture, and all the rest of it in order to get what they want. A little bit over is people who will resort to extreme coercion, but they won't actually kill you, but they will do everything they can to undermine you. A little bit further over is I'll do what I want to do and you do what you want to do, and I won't help you or anything and you won't, but we'll let each other exist. But further is getting to, yes, I'll help you and you'll help me and we'll do. And then there's the golden rule, do unto others what they want to do. But further along, you get to Ubuntu. I will help you because we together create something bigger than either of us. And further over on the spectrum is the Desmond Tutu position. I will forgive you, but further over is the Martin Luther King position and Mahatma Gandhi. I will allow myself to suffer on your behalf. And that is the only way which is called kenosis in the religious terms. Kenosis is if you are willing to suffer on behalf of your enemy. That's a truly remarkable form of ethics in which you are doing something on behalf of someone who is not your friend. They are actually trying to undermine. And Martin Luther King and Mahatma Gandhi turned this into a practical political operation, which was quite extraordinary. I've been to the Martin Luther King Museum in Atlanta. It's fantastic. And this changes it. And so a lot of people try to understand morality by game theory and all this kind of thing. This absolutely transcends that. It goes to a completely different dimension. If you have a method of turning an enemy into a friend, you're living in a completely different dimension than all of that game theory stuff. So and the point about this is you either recognize the power of this or you don't. That's all I can say. And as far as I'm concerned, this is the deep nature morality, is this idea of kenosis or sacrificing on behalf of other. And you've got this whole spectrum. And you can say very clearly where some people are. Well, I better not make some statements. I'll run into trouble.
Yeah. I'm sure game theory would never take you, anywhere close to Ubuntu, because it would be about what do I get and what do you get.
Ubuntu, we are greater together than we would be separately. But anyhow, there's a spectrum, and you can take any person, any organization, and ask yourself, where does it sit on the spectrum?
Yeah. But and I think, listening to what you just said, the unfortunate thing is that because you ended up saying it's either you get this or you don't, right? Which I think is sort of like the position we started off at, right? Because at first, you said something like, if you have these, catastrophes like apartheid or what's happening in Gaza, we can't say, if we don't believe in this possibility space of moral truths, we can't say something is wrong. But still, we end up in that same place, even if we say, we consider spirituality and these big figures that taught us these different lessons, we still end up in the same place of we can't really convince each other.
Well, I think something like this is something that you get transformed by experience. If you actually experience it, then that's transformatory. It ends. In the end, it's not something to talk about, it's something to experience.
Yeah. So I'd also like to ask you about what your position is when it comes to consciousness. Do you believe that consciousness is fundamental, so that would make you a panpsychist, or do you believe it's an emergent property of the brain? We just need to understand how neurons work. Work hard enough on that, we can build our own brain.
I'm certainly not a panpsychist. I don't believe that stones have consciousness. There's a very, very interesting document just come out from some of my colleagues about consciousness in insects and animals and so on. which is worth reading. A guy called Jonathan Birch and some colleagues have just put it out. And in terms of emergence of consciousness, there's a Mark Solms, of course, has written about this, but there's a crucial step in consciousness, which is, do animals play? And they've come out with evidence that ants play, which I think is an amazing kind of thing. And there's also a way in which ants work together to solve problems and so on. So but there's different levels of consciousness. I think that's quite clear, and a lot of people have written about this. But we have self-consciousness and we have a symbolic capacity. It's a symbolic capacity which enables us to have language to convey ideas between us. And this is the difference between us and all the great apes. But there's this core problem in consciousness, which is qualia, which is, I can hear you, you can hear me, I can feel pain, you can feel pain, and all that kind of thing. And I've looked at neurosciences quite a lot, and the hard problem of consciousness is explaining where qualia come from, and I don't think we have the beginning of an idea how to explain it. The easy problem of consciousness is saying, well, this part of the brain is involved, that part of the brain, they're interacting with each other. We can understand all of that. Signals flowing in the brain between down neurons and neural networks, all of that stuff is straightforward. In principle, it's very, very complex in practice. Brain imaging is limited. One mustn't overestimate what brain imaging can do. The very interesting stuff at the moment is the way that the computer science stuff, these chat GPT kind of things are beginning to look as if they're conscious, which is, but I don't think they are conscious. And I don't think we even have an idea how to solve the hard problem of consciousness. Now, if you are a true reductionist, you try to get around this by basically denying that the hard problem of consciousness exists. And a very famous philosopher called Daniel Dennett has just died, and there's a lot of interesting discussion about him. He tried to get around it basically by denying that consciousness existed. And he wrote a book called Consciousness Solved, and he solved it by saying it doesn't exist. And because he was a hardcore reductionist, he basically just said it doesn't exist, but pretended he wasn't saying that. And quite a lot of people have come and been calling him out. He's just died. And there have been some very interesting reviews saying his position was fundamentally self-contradictory. And if you say to me, consciousness is an illusion, that is a meaningless sentence. You can't have an illusion unless you're conscious. So if you're conscious, you can have illusions, but one of those illusions cannot be that you are conscious, because if you're not conscious, you can't have any illusions of any kind, whatever. And the problem is Daniel Dennett is this reductionist, and I've been spending the past 15, 20 years fighting reductionism and saying that things are emergent. Self-consciousness exists above a certain level. We do not know what the key difference is between our brains and the great apes, which enables us to have language, and they don't have language. They can have pre-language. They can learn a couple of hundred words and so on, but they can't have recursion. They can't have sentences which refer in a recursory way. And I think we might be able to solve that problem. I think we might be able to solve the problem of how we have language, which has not been solved. We don't even know at a certain level which is, but I think the hard problem, how we have qualia, may be irresolvable or very, very difficult. But I do know that if you deny it exists, you're going off completely on the wrong track. And that was basically Daniel Dennett's position, because the problem was he started off, his fundamental assumption was reductionist, and then he at a certain sense, he honestly followed it through. And so that led him to deny that consciousness exists. And so as a consequence, my take of this is it proves that that hardcore materialist position, reduction position, has to be false. Now, I will just mention there is another way in which it's obviously false, which is computers, and you've worked a lot on computers. And there's a wonderful little book which I have here called Computer Science, A Very Short Introduction by Dasgupta. And he talks in depth about how computers are symbolic systems and they're abstract systems, and a computer is at its heart an abstract system. A program is abstract, an algorithm is abstract, and that algorithm has causal power. So I think it is absolutely undeniable that abstract entities have causal powers. And an algorithm is an example. And you can follow this all the way through. His book is really an excellent book, which I can highly recommend. And then on the other side, you can look at this from the biology side, and I've got two books I recommend here. How Life Works by Philip Ball looks at how agency comes in biology. And this book, Free Agents, How Evolution Gave Us Free Will by Kevin Mitchell. And these are both coming from the biology side. So you can look at it from the side of computer science, which proves without question that abstract causation is possible. And then in the human mind, is abstract causation possible? Yes. The computer that you and I are using wouldn't exist unless it started in our minds. And so anybody who claims that only physical stuff has causal power is simply fundamentally wrong. They cannot explain how the computer on which we are talking to each other exists. It's as simple as that.
Yeah, definitely. So may you please let's just dwell a bit on the idea of reductionism. And you say you are not a reductionist, I suppose, because you argue that some things are emergent. So what do we mean when we talk about emergence, and how is it different from reductionism?
Okay, well, you have to, it depends on the context, but there are two contexts. The computer science, computer context is very easy because we've built them. We know all of the different levels. And you have to understand in a computer, there are two hierarchies. There's a physical hierarchy and there's a logical hierarchy. And I call them orthogonal to each other because the physical hierarchy, it's all the stuff starting off with chips and with transistors, well, starting with electrons, transistors, chips and so on, up to local networks, a global network. That's a physical network. And the logical network, you've got an application program, you've got an operating system, you've got compilers and interpreters, which take a logic at this level, take it all the way down until it's digital. So there are two different hierarchies in that case. In biology, you've got atoms, you've got molecules, you've got biomolecules, you've got cells, you've got tissues, you've got physiological systems, you've got the organ, you've got that. Now, in emergence, there is stuff which you can examine and you can represent by laws at each emergent level. For instance, the eye receives photons and turns them into signals. You can characterize how that happens at the level of the eye, or you can characterize how that happens at the level of molecules. You've got particular molecules, rhodopsin, from which light comes in and gets turned into chemical signals. And you've got genetic gene regulatory networks, and you can characterize how genes are controlled in order to produce proteins. And so there are these different levels, and each of them is emergent. And it doesn't help you if you just know the physics. It tells you nothing about gene regulatory networks. If you know gene regulatory networks, it tells you nothing about how the brain functions. So there are all of these different levels, and they are all working in concert with each other. And you have bottom-up action taking place. Higher levels emerge from the lower levels, which is what all the reductions are. But you've got downward causation taking place as well. And there are two basic kinds of downward causation. One is time-dependent constraints, and one is creating, modifying, or deleting lower-level elements. And I'll just very briefly mention the one. If you have a circuit with a battery and a lamp and a switch, okay, you turn it off, no current flows. If you turn it on, a current flows. And the constraint is that the electrical wire makes the current, the electrons flow from the start to the end. They can't flow sideways. That's actually the key point on about an electric wire. It has an infinite resistance this way. And when you close the switch, it allows the electrons to flow. When it's open, it doesn't. So that's downward causation from the switch, which is a higher level thing, down to the level of electrons. So that's a case of time-dependent constraints. The other one which happens is higher levels creating and modifying or deleting lower level elements. And this happens all the time in physics in various ways. I don't know if you know about phonons, for instance, in physics, or Cooper pairs and superconductors. Those exist. Those are created downwards. In biology, when you read my favorite example is a bear, and if you have the bear in the Arctic, in the ice flows, it'll be white because that enables it to creep up on its enemies. It's a prey. And if it's in the Canadian tundra, it'll be black or brown. And it is that context which acts down basically to tell, I'm talking metaphorically, evolution basically tells the bear it's good to have white fur or black fur. That goes down, and that's to say, okay, we better have this kind of protein rather than that one to make up the fur, and that goes down to the genes. And so the different nature of the environment chains down, right the way down, to change the elements at the bottom level. And so some bear must have walked from I don't know which way around, from the tundra to the ice flows or the other way around. And basically evolution said you better change your genes in order to get different proteins. And so the environment acted all the way down to change the elements, the genes, and to change the proteins. So that's a downward action whereby higher levels change what happens at lower levels.
Yeah. I've had Richard Dawkins say something like, by looking at the genetic code of an organism, we can be able to sort of reconstruct the environment in which it lived, right?
I'm not sure he ever said anything like that. I've got a lot of problems with what Dawkins says. I don't know if he said that. What he did say is that genes are replicators, and that is simply a biological false statement. A gene does not replicate. If you take DNA and put in a petri dish and give it all of the food it might want, it'll just sit there. Nothing will change. The replicator is the cell, and we're made up of billions of cells, and cells are what replicate, not genes. Genes cannot and do not replicate. When Richard Dawkins has made that statement, he's made a very simple biological error.
Does that statement, the statement that he made about genes being replicators, does that also then affect his argument about the selfish gene?
Well, he seems to have this. He seems to be assigning genes with agency. The gene is telling you to smile or to be good or to be. That is simply not the way things works. What is very important in downward causation is multiple realizability. And this is the same in computers. Let's take a computer example. I can have a high-level language, a word processing program. I can write it in Fortran or in Lisp or in Algol. I can go down. I can write it in the language of any chip. The chips will have different coding and so on. And there are many, many different ways to do things at lower level. It's the same in biology. If I'm going to create an eye, it needs certain gene regulatory networks, certain genes, but there's billions of different ways you can create an eye at the lower level. And this is basically what Andreas Wagner's book is about, is the way there's huge number of genes. And if you take a look, firstly, agency only emerges at the higher levels. There is no agency at the level of genes. Genes are not agents. Cells, single cells organisms are, and cells do work. So cells are agents, but nothing at a lower level is an agent. And certainly genes aren't little things wandering around with a smile on their face making things happen. That's just not the way things are.
Yeah.
He personifies genes, and that's a fiction.
When you talk about now, you mentioned that there could be multiple ways to realize the same thing at the high level, for example, an eye.
Yeah.
Do you then think that it's possible, if it's possible for a different kind of genetic code to have evolved on this earth to create?
I think we know it would have been possible for a different kind of genetic codes. I think people have tried that. But what I do not believe, people have asked, could life be based in silicon or some other thing? I don't believe that for a minute. I believe it has to be based in carbon, because polypeptide chains have got these extraordinary properties. The way that they fold, biology is based in the folding of proteins in an absolutely fundamental way. Proteins change shape, and in the end, the way that we're talking to each other is based in proteins folding and unfolding all of the time. And it's based in ion channels opening and closing, allowing ions to travel in and out of neurons. And those things are what Philip Ball emphasizes in that book of his is the immense stochasticity of biology. This is where it's completely unlike a digital computer. There's a vast amount of variability at the low levels, and biology has discovered that, and metaphorically speaking, has made great use of that. And in order to attain a higher level goal, even the reading of the gene, we used to think it was a very simple process. In that book I've mentioned by Philip Ball, he explained there's a vast amount of variability in the way it takes place, but that variability results in very reliably obtaining the desired high level goal. And this is all driven from the higher level. It's driven downwards, which is the key nature of biology. And so, for instance, it is crucial advantage in evolutionary terms to be able to see. There are different ways of making eyes. There's billions of different ways genetically of creating eyes. I'm sorry. But that is driven downwards. It's driven by physiological needs and by ecological needs.
Yeah. So another thing I'd like to ask about is the idea of time. Do you consider time to be a human conception, like a convention, or do you think time, another way of asking this question is, exists independently of us?
Yeah. Okay, my position is very clear. Time exists independently of us. We apprehend it through the human mind, and our mind is, at a certain level, acts as a clock, but it's a very unreliable clock. So that sometimes time can seem to pass very fast. Famously, some kind of accident is about to happen, and you see this wall coming up towards you, the car has gone off the road, and it seems to take a very long time for that to happen. And so, and you get bored, and it seems time is taking forever, and so on. So the time is a clock, but there's many, many oscillations taking place in our brains. In fact, oscillations are one of the basic biological phenomena, but there's no reason that they would be accurate timekeepers.
Yeah. By accurate timekeepers, there, I suppose you mean they would measure the same unit of time equally, Yeah. And so why is the idea or the ideas of space and time so important in physics? And I think what I mean by that question is, if I were to wake up tomorrow and I was tasked with the project of starting physics, I don't think I would have thought, okay, space and time are going to be two very important ingredients in my exploration. But it seems they have become so important in the workings of physicists? Why are these two ideas so important?
Well, but they're basically taken for granted in ordinary physics. If you write down Maxwell's equations, it's got time derivatives, got spatial derivatives. Newton's laws of motion, it's the same thing. There were the two revolutions, the special relativity showing that simultaneity depends on your motion and that rate of measurement of time depends on your motion, and that was the first revolution. And so time is more complicated than we thought it would be. And then general relativity came in and with a more fundamental understanding of the nature of time, and that, for instance, if you have a big tower, time goes slightly slower at the top relative to the way it goes at the bottom. But again, it's perfectly understandable. The clock at the bottom is measuring time there, the clock at the top is measuring time there. There's a relation between them, which you can understand. And then space-time is curved, and that brings in a whole lot more complications. But you describe space-time by something called the metric tensor. And the metric tensor is a quantity with two indices. And if you know the metric tensor, you can determine time along any path and space along any path. So in space-time, there's the metric tensor, and then the Einstein field equations tell you how the matter around determines the metric tensor. And space-time isn't flat, which results in things like black holes where you drop something in and it can never get out, and that kind of stuff. But the basics on which all of physics is expressed is the basic physical laws all are expressed in terms of space and time derivatives.
Yeah. So about a few years, but 2-3 years ago, as I was doing my master's research, I came across this quote, which is, "All observation is theory laden," and I think it's attributed to Karl Popper. That is, all observation is theory laden. So this was a bit disheartening to me. I think I was a bit naive at the time. So I was sort of like, oh, so if I'm pointing these cameras and the sensors at things and I'm collecting this data and I'm drawing conclusions, but these conclusions that I'm drawing are sort of like inextricably tied to the theories I have in my head rather than the data itself. Do you believe like that all observation is theory laden? And if it is, how do you sort of alleviate the fears of a young scientist or researcher who worries that like, oh, okay, this is going to be a difficult endeavor?
Yeah, look, all observations are theory laden in that sense. You've got a concept of time, you've got a concept of space, you've got concepts of current, of charge, of temperature, and so on. And each of those is defined in a particular way, and underlying that is a theory which results in a statement: if you do this and this, you will measure the temperature. But they are based on an underlying theory, and I don't think there's any way of getting around that. The aim is to get a consistent system. So you have a system of defining the measurements, and it's all of these things. And then that system of measurements gives you laws which work and describe the way that things actually happen. Of course, there was recently a total re-evaluation of the fundamental system of measurements. A good friend of mine was involved in that, and you try to relate them to very, very fundamental measurements. And that's an ongoing process. There's a length used to be defined by the length of a bar of iron kept in Paris. We're no longer doing that. And so there's and I'm not an expert in metrology, but my friend Jean-Philippe Uzanes, and there are very, very precise measurements and which settle fundamental units of time and space. And basically, what you require is that the system works out consistently. And if at some point it started being inconsistent, one of the things you go back and do is relook at the issue of measurement. We're probably close to being at the end. Let me mention just one other thing which I think is interesting. A recent paper I wrote, some of the scientific fundamentalists talk about the wave function of the universe. And the wave function of the universe is supposed, there are various interpretations, but some people write about something called the Wheeler-DeWitt equation, which my colleague Stephen Hawking wrote about. Other people use the Schrödinger equation. But it doesn't matter. What they're doing is they're trying to reduce physics to a quantum theory description. And the crucial point about the Schrödinger equation, it's a linear equation. Now, you've done some mathematics courses and you've learned about linear equations. And the point about a linear equation is what it can do is really very, very limited. If you ask yourself what goes on in the real world, the answer is actually there's nothing out there which is linear. So we have a fundamental problem. If everything is based in a linear equation, how on earth can nonlinear things take place? And these colleagues of mine talk about the wave function of the universe, and because they're so wedded to this theory, they try to pretend that everything out there is linear. That ends them up with something called the Everett multiverse, in which wave function is branching all of the time, and there's billions of copies of this universe, and you have copies, and they talk about multi-minds and a whole lot of stuff. Okay, I don't believe a word of that. The solution to this problem is something which we discover in general relativity, is that in general, when you have a space-time, you can't cover it by a single coordinate patch. And in fact, a simple example is the Earth. A two-sphere like the Earth has got a coordinate singularity at the North Pole and at the South Pole. All of the lines, you can't say what the latitude of the North Pole is because all lines, there's a coordinate singularity. Now, the way you have to get around this is use 2 or 3 coordinate patches to cover it. And then, so you say, we have an atlas of coordinates, and each coordinate patch covers a bit. The atlas as a whole covers the whole, and where they intersect, you describe how the 2 coordinates relate to each other. Now, I believe that the same is true in quantum theory. There is no single wave function for the universe as a whole. I think that's simply untrue. What there are local wave functions. And the local wave functions, they cover local regions of space-time. And what you can do is ask yourself, in how big a domain is the physics linear? And that is the maximum that this little wave function can do. Then you put another one, and you cover the whole of space-time with little local wave function domains, and within each of which dynamics is linear. And where they overlap, you relate them to each other by basically a coordinate transformation. And in technical terms, it relates to something called a Bogoliubov transformation between Hilbert spaces. And this enables me to get around this whole problem of how a linear theory, namely quantum physics described by the Schrödinger equation, can underlie all of this nonlinear stuff. And what that means is there is no such thing as a wave function of the universe. There's no such thing as a wave function of a brain. Your brain is incredibly nonlinear. Not the faintest hope could be described linearly. There isn't a wave function for a cat, so you've probably read a lot of stuff about Schrödinger's cat. There is no wave function for a cat. And I've written a little paper about this, which you can find through Google Scholar if you look up what I've written in Google Scholar.
All right, Prof. One last question from me. So you turn 85 this year, and when you sit and blow your 85 candles, what will you sit and consider, looking back, your proudest achievement?
my proudest achievement. I'm a synthesizer, and in the long term, I will be proud of this work I'm doing now in synthesizing stuff. And now I've got a contract from Oxford University Press. I'm writing a book which should be, I'll deliver the manuscript in October, called How We Come to Be, Everything That Leads to Our Existence. And the emphasis is on the word everything.
Everything.
But there's a very ancient paper I wrote in 1967. And Kurt Godel, you know the name Kurt Godel?
Yeah. The guy who broke mathematics.
Greatest logician of the last century. He wrote various absolutely fundamental papers, but when he was at the Institute of Advanced Studies in Princeton, he talked with Albert Einstein about general relativity, and he wrote two very, very interesting papers about general relativity. And the one paper was about a closed time, like Einstein's the Gödel universe, and that got Einstein very upset because in the Gödel universe, you can travel into the past. And people had thought before general relativity would prevent that, but it doesn't. And Gödel showed that, and Einstein was very upset by this. But what's not so well known is Gödel wrote a paper on cosmology. Very, very interesting paper when he talked about rotating universes. And he proved a theorem that in the case of these spatially homogeneous universes, if the universe is distorting, it can't both expand and rotate. So if the distortion is zero, either it can expand or it can rotate, but it can't do both.
Yeah.
And I looked at this. It was one of the things I looked at in 1966. I studied it deeply, and I generalized the theorem. He proved it in the case of spatially homogeneous universes, and I proved that it was true in general.
Okay.
And so my proud statement is the following: I'm one of the very few people on Earth who have generalized the theorem of Gödel.
Yeah.
Not a logical theorem, but a theorem in general relativity. And that little paper of mine has resulted in a lot of follow-up papers. And it's related to all sorts of things in general relativity, which I don't have time to go on here. But
Yeah.
I think that's a nice statement that I can make.
Yeah. Thank you. Thank you so much for sharing and agreeing to come here. I had a really interesting time talking to you. There's a whole lot of questions that I would have asked you, but I didn't have the time because you're so generous with your responses, which I appreciate. Yeah.
Look, as a computer scientist, do yourself a favor and read this book by Das Gupta, Computer Science. It's a very deeply thought out book. In particular, he's very, very good about this issue of computation being abstract.
Yeah.
And that's fundamental to computation.
Yeah.
Given that computers can cause things through abstract, it proves that abstract causation exists. And that totally undermines the reductionist presupposition that only physical things can have causal effects. It's not true. Abstract things can have causal effects.
Yeah. That's an opinion I think I agree with, actually. But yeah, I'll be keen to read the book. I'll definitely get it. Thank you for the recommendation.
Thank you very much.
All right. Bye.